In today's lecture, I'm gonna give you a fairly brief summary of the different types of chemical equilibrium, most of which I expect you covered in Chem 1 or 2. But I think it's good to remind you of what is expected of you that you need to remember from your Chem 1 or 2. So we're gonna talk about the different types of chemical equilibrium as well as their relevance. So the learning outcomes in this segment is that I'd like you to appreciate the importance of the chemical equilibrium as a basis actually of all chemistry actually that you'll ever learn or that you've actually ever learned. Now I'd like you to be reminded of the foundational manipulation of chemical equilibrium, calculations. I also like you to appreciate the applications of chemical equilibrium in quantitative chemical analysis. We can divide different types of chemical reactions out there and chemical equilibria into 5 categories. Now there's what you call the acid-base chemical equilibrium. And of course, you're going to see that each of these chemical equilibria, they are characterized, by a constant that we call equilibrium constant. So you've got the acid-base reactions, and they're going to be characterized, by Ka, which is the acid dissociation constant, the Ka or the Kb. Now, you also have the solubility product, which is characterized by the Ksp. We also have the complexometric equilibrium, which is characterized by what you call the Kf, or what people often refer to as a formation constant. And you also have the redox equilibria, often characterized, by the Keq, equilibrium constant. And lastly, you've got the phase distribution equilibria, or what you call the Kd. I'll take note of this. Of course, I've only highlighted a few relevant applications in real life of these different types of chemical equilibria. For example, in acid-base equilibria, you come across, it in lots of different environments, be it in the environment, be it in human or animal physiology and so on. A good example, is most drugs out there, aspirin, acetaminophen, dextromethorphan, and so on. Most of these drugs, or cocaine, most of these drugs, are either acids or bases. And their solubilities and metabolics, when they are consumed, is dependent, on the acid-base reactions, that happen within, the physiological system. The acid-base equilibria is also the basis of the buffer systems, that make sure that we are not acidified, when we take, for example, fairly acidic foods and so forth. So very, very important, in lots of mechanisms in the environment and so on. Maybe a good example for solubility product equilibria is a major problem of the acid rain. That, with the pollution, you get the acid rain, and then there is a destruction of the calcium phosphates, that make up the ocean coral reefs. And that has been a major problem out there. And of course, we know the coral reefs are major habitats, for lots of different types of marine animals and organisms. Now, complexometric equilibrium, maybe a good example is when somebody gets poisoned with the heavy metals. Often they would consume, or they would be given some ligands, such as humic substances and so on, that chelate the heavy metals and they make them fairly soluble, so that somebody can actually excrete them. Now, you guys already did the spectrophotometric determination of iron in the lab, and actually you did this type of reaction where you took the iron and you reacted it with bipyridine, and that is complexometric equilibria. The iron was complexed, with bipyridine, and the KEF formation constant for that reaction was fairly large, and that's why the bipyridine reacted very quickly, with the iron. Now, redox equilibria, on the other hand, and we're going to come across it a lot, most elements exist in different oxidation states. I'll give you an example. Arsenic, they can exist in arsenic 3 or arsenic 5. And their toxicity, is dependent, on their oxidation state. And, redox equilibria, which is the basis of how you oxidize different chemical species or reduce different chemical species, is the overarching type of chemistry, that determines the different oxidation states in different metals. And like I said, oxidation states determine, the toxicity, of different types of metals. For example, arsenic 5, very, very toxic, compared to the arsenic 3. Talk about, chromium 6 plus, and chromium 3 plus. Chromium 6 plus, is very, very toxic compared, to the chromium 3. And lastly, we got the phase distribution, and maybe a good example of its relevance is, how we decaffeinate coffee. How do you remove caffeine, from coffee for those people who are not tolerant, to caffeine? And typically, you use chromatographic techniques, such as even liquid chromatography, where caffeine partitions, between two different solvents, in which in one solvent caffeine is more soluble, prefers to be in that solvent, and that partitioning is what you call the KD. In fact, another way of calling the KD is partition coefficient. Partition coefficient is another name for distribution coefficient, or the KD. Now, we all know that reactions, look like this. You have the reactants, and after the reaction, you get the products. And typically, a generic chemical reaction would look like that. The way you would calculate, the equilibrium constant, or the K's that we talked about in the previous slide, is where you take the concentration of the products raised to their stoichiometry divided by the reactants raised to the stoichiometry of the reactants. So it's very, very critical then, to know the stoichiometric nature, of your reactions. So before you can calculate equilibrium constant, you should be able to know the stoichiometry of that reaction. So that reaction should always be balanced. Make sure, it's balanced. The number of atoms, on the left-hand side should be equal to, the number of atoms, in the right-hand side. Now, another important thing that I'd like you to remind you is that as reactions happen, they undergo what you refer to as, kinetics. Some reactions, happen very, very quickly, meaning the forward reaction is very, very fast. But remember, reactions are always in a steady state, meaning, the products are being formed, but also that reaction in most cases is also going in the backward direction. And often you would wait, for a given amount of time for equilibrium to be established. So for very fast reactions, equilibrium is established, fairly quickly. And so, the K, equilibrium constant, can equally be quantitatively defined, as the reaction constant, the Kf, as a reaction constant in the forward direction divided by the rate constant, in the backward direction, the K. But so take note of that. There's a difference between the rate constant and the equilibrium constant. The rate constant only tells you how rapid that reaction is going, maybe in the forward direction, but it doesn't necessarily really tell you about, the thermodynamics behavior of that reaction. So the thermodynamics behavior of the reaction, is characterized, often by the big K, the equilibrium constant. So I hope that's clear. This equilibrium really refers then, to the period, to this steady state, where the forward rate is equals to the backward rate. All right. So equilibrium refers to the point or the time at which the forward rate of the reaction is equals to the backward rate, of that reaction. Okay. Now, the equilibrium constant, based on the way we calculated it before, the concentration of the products raised to their stoichiometry divided by the concentration of the reactants raised to their stoichiometry is actually an approximation. It's not completely true. Ideally, the equilibrium constant, should be calculated as follows, where the K, or the equilibrium constant, is equal to the activity of the products raised to their stoichiometry divided by the activities, of the reactants raised to their stoichiometry. And we all know activity, is calculated as follows. So the activity maybe of product C is equal to the concentration of that product multiplied by what you refer to as the activity coefficient, the activity coefficient. And the activity coefficient, is proportional, to the root of the ionic strength. So the good news is, the reason why we do this approximation is because in most cases, the activity coefficients, are very, very close to 1. So the activity coefficients in most cases are very close to 1. And that's why we make this approximation. However, in some cases, depending on the ionic strength of that solution, the K might be fairly different. So take note of that. The K that we often calculate based on the concentrations is often an approximation where we assume, that the activity coefficients, are fairly close to 1. Again, remember, the activity coefficients are proportional to what you refer to as the ionic strength. So how do you calculate the ionic strength? And hopefully as we go along, you're going to see the importance of the ionic strength, this mu. The way we calculate the ionic strength is based on this simple formula that you take a half of the summation of the concentration of the respective ions of a particular salt, and of course you multiply the concentrations of those ions with the charge of that ion squared, and after you do that summation and you divide by 2, that's how you calculate the mu or the ionic strength. Let me give you an example, maybe with this kind of a problem where you're asked to calculate the value of the ionic strength in this solution. So you've got 0.1 molar of sodium chloride and 0.1 molar of sodium sulfate, 0.1 molar of magnesium sulfate, and a combination of A and C. And you're going to see, despite the fact that the concentrations are the same, the ionic strength of those solutions are different because the ionic strength is dependent, on the charge state, of the respective ions in those salts. So as you can see from the definition, the ionic strength is equals to a half of the summation of the concentration of the respective ions, and you multiplied that, by the charge state. So if at all you've got sodium chloride, for example, we know when you dissolve it, it's gonna dissociate into sodium ions and, chloride ions. For every mole, I think initially we had 0.1 molar. For every mole of sodium chloride, you get the same number of moles, or the same concentration, of sodium, and the same concentration, of chloride, of 0.1 molar. And then after that, now you can substitute it, in this reaction. You can see the concentration of sodium is 0.1. I multiply it by the charge. The charge of sodium, you can see it's 1. And I square that, plus the concentration of chloride, you can see it's 0.1. I multiplied by the charge, which is -1 squared. You can see that. And then I divide all that by 2 after I do the summation. And you can see the ionic strength of sodium chloride then is 0.1. So same thing with sodium sulfate. You take the sodium sulfate, and we know for 1 mole of sodium sulfate, I'm getting 2 moles of sodium ions, and 1 mole, of sulfate, 1 mole of sulfate. So again, I substitute in my ionic strength calculation a half, and then the summation of the sodium ions. In this case, the concentration is 0.2, because for 1 mole of sodium ions, I get 2 moles of sodium ions. So 0.1 multiplied by 2, I get 0.2, and the ion charge state, is +1, I square that, plus the concentration of sulfate. For every 1 mole of this, I'm getting just 1 mole of this, so this is 0.1 molar, so you can see that. But then you can see in this case, the charge is different. The charge of sulfate is -2, so -2 squared, and then I do the summation. And then you can see that the mu, the ionic strength, is 0.3. And you can do the same for magnesium sulfate. We know magnesium has got a 2+, sulfate is 2+. The concentration is for 1 mole of magnesium sulfate, you get 1 mole of magnesium ions, and so forth. And so you can do the calculation that way, and you see that the mu, for 0.1 molar of magnesium sulfate is 0.4, and that's the ionic strength. So you can see for the same concentration of salt, you've got very different, ionic strengths. Now lastly, if you have 2 salts and you are dissolving them and mixing those 2 solutions together, like salt 1, which was sodium chloride, and the other salt, magnesium sulfate, and you are mixing them, all what you need to do is add up the ionic strengths, the 0.1 ionic strength and the 0.4 ionic strength for magnesium sulfate to get the 0.5 magnesium sulfate. Maybe somebody is going to ask, why is this important? Ionic strength is so important, especially when you're doing potentiometry. And a good example of potentiometry, which is an analytical method where you're measuring the voltage associated with the concentration of a particular species. A good example is when you're doing pH. pH, maybe the simplest example of potentiometry, when you're measuring pH using a pH electrode, which all of us have used. You're gonna see that if you take the pH of seawater that has got exactly the same hydronium ion concentration, which you're measuring with a pH electrode, and has got the same amount with the fresh water, the results are very, very different because of the ionic strength. The seawater, it's got a lot of salt in it, so it's got a high ionic strength. whereas the fresh water, it doesn't have a lot of ions in it, and so it's got a very low ionic strength. And because you're measuring, the conductivity really, of that solution, and that's what you're measuring, with potentiometry. You're really measuring, the voltage, the conductivity, of that solution between two pairs of electrodes. Then you're gonna see that the ionic strength, makes a very huge difference when you're doing those types of measurements. So I guess the moral of the story is, don't just take a pH electrode, go dip it, in the ocean, and then go dip it, in a river water, and imagine that the results are accurate. They are not. And so we need to make sure that the ionic strength of the solutions that we are measuring are very, very similar. So the other thing that we're going to talk about is solubility product, the KSP. And the solubility product really refers to the equilibrium constant of a reaction where you take a solid salt and you dissolve it in water up to the point of saturation, meaning you cannot dissolve more salt. So that's the only time, where the KSP, or the solubility product equilibria, is satisfied. So the solution, must be saturated. So you take a salt, which is a solid, you dissolve it in water, and we all know if you dissolve a salt in water, there is dissociation of the ions into the constituent ions that made up the salt. And of course, the stoichiometry, is fairly well known. And if that's if that solution is saturated, then the equilibrium constant, is referred to as, the KSP. The KSP, this one here. So the KSP again is calculated as follows: the product's concentration, raised to their stoichiometry, divided by the product. However, because the product really here is a solid and it's in a standard state, we often, neglect, the denominator. So in essence, the KSP, is equals to, that, just the products. Is equals to just the products. So we neglect, the reactant. So how do you determine the KSP? And you guys have seen, the constant, the KSP constants, out there. How do you really determine it? How do people know the KSP? You do that experimentally. Assume you really want to determine the KSP of barium sulfate, which is a salt, and the molecular weight of barium sulfate is 233 grams per mole. All right, and so where you would do this to determine the KSP, you would take the salt, add it in known volume of water, until you cannot dissolve more salt, and then after that, you can measure the respective concentrations of barium ions and the respective concentrations, of sulfate. And after you do that, we already know that the KSP is equals to the constituent ion products, the barium 2 plus raised to their stoichiometry, because in this case you can see it's 1, and in this case it's 1 again. For 1 mole you get 1 mole of barium, 1 mole of sulfate, and you can do the calculations that way. So from the salt that you measure, you can measure the constituent ions of barium, maybe using ICP. You can measure the constituent concentration of sulfate in this case, possibly using chromatography, ion chromatography, and then you determine that, you plug it in the equilibrium expression, and that way you can calculate the KSP. So the KSPs, the point is, are experimentally determined. Dissolve the salt and then you determine the respective concentration of the ions. So in most cases, when you're doing solubility product calculations, like I said, we must make sure that the solution is saturated so that you can have the equilibrium expression for solubility product satisfied. Otherwise, there is an error in that. And so we use the solubility product calculations often, to calculate or determine the concentration of one species if the other is already known. I'll give you an example. So what's the concentration of silver ions in equilibrium with 0.1 molar of sulfate? So that one is already known, in solution, that contains undissolved silver sulfate, meaning this one is already satisfied, is already saturated. We already know, that to generate the equilibrium expression or the reaction would be the salt. It dissociates into its component ions. For 1 mole of this salt, you're getting 2 moles of silver ions and 1 mole of sulfate. The KSP is equals to the product raised to their stoichiometry. You can see that. But in this case, you're going to see that I already know the concentration of sulfate, which is 0.1. So I can substitute it here. The KSP is already known. It's 1.4 times 10 to the power minus 5. And so I can calculate the concentration of the silver ions that are in solution in this salt, based on that simple expression. Now take note of this, dissolution or solubility, molar solubility, differs when you are doing it in pure water, when you are dissolving a salt in pure water, or when you are dissolving a salt in another solution containing a constituent ion of the salt. The solubility differs. It's very important. And that's what we refer to as, the common ion effect. When you take a salt and dissolve it in a solution that already contains one of the constituent ions of that salt. And the solubility changes. I'll give you an example. You've been asked here to calculate the molar solubility of silver carbonate in a solution that is 0.2 molar of carbonate. And so determine the solubility in pure water and compare it to the solubility, in this solution. So you can see up here, again, what I need to do is write up the reaction that is taking place. The silver carbonate is dissociating into silver. For 1 mole, I get 2 moles of silver and 1 mole of carbonate. But I'm dissolving it already, in a solution, that has got 0.2 molar. And so the change in equilibrium then is gonna be, for 1 mole I get 2 more, so that's a 2x. And for 1 mole I get just 1 mole of the carbonate, so that's plus x. And so the equilibrium then is gonna be 2x, and then in this case it's gonna be x plus what was originally present, the 0.02. And then I can just fit it, into the equilibrium expression. I already know KSP. So this one I already know from my equilibrium expression is 2x, of course, raised to their stoichiometry. And I know the concentration here, 0.02 plus x raised to the stoichiometry is the concentration of the carbonate. Now remember, you can go ahead and solve the quadratic equation. You can see this is a quadratic equation when you expand this. However, you can simplify this expression. You can make an assumption, that 0.02 plus x is very similar to 0.02, meaning the x is very, very insignificant. Meaning the dissociation is very, very insignificant. And of course, we know that that is dependent, on how big or small the KSP is. And we're going to see that. So make the approximation that 0.02 is much higher than the x and so the x is insignificant. And so you can see now the expression, reduces to this, meaning we don't really need to solve the quadratic equation. And then after you solve that, you can see that the x, I get, 1.0 times 10 to the power minus 5 molar concentration, of this. Now, sometimes it's easier because you're dealing with very, very small numbers to take the negative log of that, what you call the px, the negative log. Remember p is what you call the negative log, is a symbol. P, small p, is a symbol for negative log, so that you're dealing, with whole numbers. So if you take the negative log of this, you're gonna see is equals to 5 or 4.997. And so sometimes you take the negative log just to make it easier when you're dealing with very, very small numbers. Now remember, it's always very important to go back here and confirm, is our approximation here valid? Alright, so the 0.02 plus what we calculated here, is it approximately the same as 0.2? And we do that by what you guys know as the 5% rule. So I take the x that I calculated, I divide it, by the 0.02, the solution concentration, that I was approximating, that is much, much higher than what dissociated, times 100. And if that number is much, much less than 5%, then my rule, holds true. My 5% rule holds true, which it does. You can see it's 0.5%, and so this is correct. This is correct. And so you can see that this is what you get when you dissolve this salt in a solution that already contains a constituent ion. On the other hand, if we were to dissolve it only in water, you're gonna see that the KSP is equals to this. We already know that. You set up, the molar solubility, for 1 mole of this, you're getting 2x. For 1 mole of this, you're getting 1 mole, which is x. And then you can just substitute it, into the equilibrium expression. You get that. And then you calculate the x, you're gonna see is 1.27 times 10 to the power minus 4. So you can see it's a major difference. It's an order of magnitude, more soluble. You can see this one is much more soluble, than this. And so the common ion affects solubility. If you dissolve things in pure water, they dissolve more than if you dissolve them in salty water, that contains the constituent ion. I hope that's clear. Very important. And hopefully you can see why, if at all I've got a constituent ion here, based on Lichetarius' principle, you can see that, the equilibrium largely is gonna be pushed back, in the backward direction, because I already have the constituent ion. And you can see why this one is less soluble, compared to when you're just dissolving it in pure water, because of Lichetarius' principle. So one major application then of solubility product equilibria is separation. Like we've been trying to say many times, when you're doing analysis, your sample, in almost all cases, contains a lot of matrices in it. And we've said one way to remove matrices, is to do precipitation. Of course, we already said, for a calibration, one way to address matrix effects is to do standard addition calibration. And so to do separation, using precipitation, you can use this principle of solubility product equilibrium. Okay. And so you often have to think, am I able to separate one salt, from the other quantitatively, so that they do not co-precipitate. And that's what I'm gonna show you, in the next slide. Now assume I've got two salts, like this, iron 3+, and magnesium 2+. and they are already present, maybe in water, in seawater, and the concentration in that sample of each one of them is 0.1 molar of each of those cations. So the question is, can I separate, the iron and the magnesium? Can I resolve them, so that I can do the analysis? Yes, you can, using precipitation, solubility, product, equilibrium. I just need to add sodium hydroxide or hydroxide, and we know the iron is going to react with hydroxide to make a salt that is very insoluble. On the other hand, magnesium is going to react, with hydroxide, that I add, and it's going to make magnesium hydroxide, again, which is very insoluble. Take note of this, that these reactions, the K, I'm calling it, the K is equals to 1 over KSP, all right? Because you can see in this case, I've got the ions, and they are making the salt. So it's sort of the reverse, of the KSP. Okay, and anytime you reverse a reaction, you just need to take the inverse of the equilibrium constant. So remember that. So the first thing then I need to do is to determine which salt really precipitates first. I already know the KSPs for each of those salts. So which salt precipitates first? By rule of thumb, the lower the KSP, the lower the solubility. So you can see the KSP for this guy, the iron hydroxide, is very, very low compared to magnesium sulfate. So we can sort of, imagine and approximate, that this guy, the iron hydroxide is going to precipitate fast. However, we need to be sure. And the way to be sure is to calculate the molar solubility, all right? And you can see the molar solubility, like I said, is just the reverse of these reactions, where I take, the iron hydroxide, it dissociates into its component ions, and the magnesium hydroxide dissociates into its component ions, and the equilibrium constant, you can see now in this case, is a KSP. We know the change at equilibrium would be for 1 mole of this salt. It gives me 1 mole of the iron and 3 moles of the hydroxide. And then I can use my KSP expression. The KSP is equals to this. And I can substitute, my respective equilibrium concentrations, the X raised to a stoichiometry, which is 1 in this case. And for the hydroxide is a 3X raised to a stoichiometry, which is 3. And you can see after I do my calculation to determine the X, I get 9.27 times 10 to the power minus 11 molar concentration. On the other hand, I do the same thing. You can see that the expression is balanced, the reaction is balanced. I feed it into the equilibrium expression, and I get the X being equals to 0.000121 molar concentration. So you can see that this one is very insoluble, very, very small compared to this. So you can see that my iron is much, much insoluble, compared to the magnesium hydroxide. And so in essence, you can add the hydroxide and the iron precipitates, you remove the precipitate, possibly even gravimetric analysis. You can go onto the analytical balance and weigh it, and then continue to titrate, continue to add the hydroxide to the solution now that only contains the magnesium. And then after that, you're going to have the salt, the magnesium hydroxide, precipitating. So you can see that you can separate two ions that were in solution and separate them sort of, into two different species that you can analyze them separately, using, for example, your analytical balance, which is called gravimetric analysis. Now, but there's a question, but can they be separated, without co-precipitating? It's very important to check that. We know that this one precipitates first, but cannot be separated, without completely, without precipitating, the other salt. And yes, you can do that. So we already know that the iron concentration is 0.1 molar. We need to determine how much of hydroxide is needed to satisfy the solubility product equilibria, for iron hydroxide. So we set up the equilibrium expression. We already know the iron is 0.1 molar. So how much of hydroxide do we need? And we can calculate it, and you can see that it's 3 times 10 to the power minus 13. And like I said before, sometimes it's easier to take the negative log, or what you call the p, small p, of OH in this case, just to make it easier, to visualize. That the number here is 12.55. All right. So the next thing you do is check at this concentration, when we've just precipitated the iron. All right. The hydroxide is present, at this concentration. At this concentration, then, have we exceeded, the KSP of magnesium hydroxide so that we can start precipitating, the next salt? So you just need to calculate what you call the QSP. And you can remember, the QSP is calculated exactly the same way as a KSP. The only difference is the QSP is the constant, before equilibrium has been established. So you've not given it enough time, for equilibrium to be established. Okay. So when you're doing, so it's almost like when you're doing the reaction, so you're right here in time, for the QSP, and the KSP is right here in time because you give it enough time, for equilibrium to happen. But the calculation is done exactly, the same way. So the QSP then of magnesium hydroxide is equals to this. We know the solution has got 0.1 molar concentration, and at the point when we've just finished precipitating the iron hydroxide, we have about 2.79 times 10 to the power minus 3 of hydroxide present. So we put it into that expression here, and then we can determine the QSP of magnesium hydroxide, at this point when you've precipitated this is equals to that. And then you can check, is a QSP at this point when you've just precipitated the iron hydroxide, has it exceeded the KSP? And so has magnesium hydroxide started to precipitate? And you can see that the QSP is much, much smaller, than the KSP. In fact, 2 orders of magnitude smaller. And so yes, it's possible, to separate, the iron from the magnesium, because we've got a very, very big difference between the QSP and the KSP. And so basically that's how you do it when you're trying to determine if you can quantitatively separate 2 species. So you compare, the QSP at the point of precipitating the first solution, and you see if at all it's been exceeded, for the second salt. So the next part, of the lecture is to talk about titration. So you can see what I've just done there before is a titration per se. It's really a titration, only that, instead of determining using volumetric analysis, in this case, I just did precipitation and used an analytical balance. But you're gonna see a more accurate way of doing quantitation of, say, 2 different salts that can easily be precipitated. A more accurate way is using what you refer to as volumetric analysis. And that's what you call titrations, really, volumetric analysis, where you're measuring, the volume of the titrant. And I'm gonna cover volumetric analysis based on solubility product equilibria in the next lecture.